Hi everyone. In the last class, we discussed some important properties of the approximate band spectrum. Today, we are going to discuss some important consequences for the result that we have proved in the last lecture. For example, we proved the following result that if T is a bounded linear operator on H, then the following are equivalent. There exists a lambda in the approximate point spectrum of T such that mod lambda equal to norm T, that is equivalent to the fact that norm T equal to the numerical radius of T. Now we have already seen that when T is self-adjoint, norm of T and numerical radius of T are same. So from this result we can say that whenever T is self-adjoint, there exists a lambda in the approximate point spectrum of T such that mod lambda equal to norm T. So immediate corollary we can write, let T be a bounded self-adjoint operator, then norm T is in the spectrum of T, or minus norm T is in the spectrum of T. Let us look at the proof. So T is self-adjoint implies numerical radius of T and norm T are same. This we have already proved in the earlier lectures. Now this implies that there exists lambda in the approximate point spectrum of T, and since T is self-adjoint, this is exactly spectrum of T such that mod lambda is norm T. Now we know that spectrum of T is subset of R, as spectrum of T is subset of R. So we get lambda is plus T, or lambda equal to minus norm T. Okay. Now since lambda is coming from the approximate point spectrum, so we consider spectrum of T and approximate point spectrum of T are same. So we get that either norm T is in the spectrum of T or minus norm T is in the spectrum of T. In fact, when T is self-adjoint, we can say that the spectrum of T is non-empty from this result without using the Gelfand-Major theorem. Okay, this is a different proof of for the fact that different proof for the fact that spectrum of T is non-empty. Okay, let us look at a few more consequences. If T is a bounded operator such that numerical radius of T and norm T are same, then we can say that the spectral radius and norm T are same. Okay. Numerical radius of T equal to norm of T implies that there exists some lambda in the approximate point spectrum of T such that mod lambda equal to norm T. This follows by the earlier theorem. So hence we can have norm of T is mod lambda, but mod lambda is less than or equal to spectral radius of T, but we know that spectral radius is always less than or equal to norm T, or we can say that spectral radius of T is exactly norm of T. Okay, now we can ask the question, what will happen to the converse? So in other words, Is it true that if spectral radius of T and norm T are same, then numerical radius and norm T are same? So the answer is affirmative in this case. This can be proved easily. You can try this proof. Okay. So these are the two important results. Next, we want to show that if T is positive as a corollary, if T is positive, then norm T is in the spectrum of T. So this directly follows from the earlier corollary. Whenever T is self-adjoint, either norm T is in the spectrum of T or minus norm T is in the spectrum of T. So we know that if T is positive, then we can say that spectrum of T is contained in 0 norm T, closed interval. Okay. Now by the earlier corollary, norm T is the spectrum of T. Okay. Next we discuss about normal operators. So we can write as a theorem. If T is normal, then we can conclude that the numerical radius of T and the norm T are same. This result we have proved for self-adjoint operators earlier. So we prove this result for normal operators. Now using the earlier theorem that we discussed, that is, there exists lambda in approximate point spectrum of T such that mod lambda equal to norm T if and only if the numerical radius and norm T are same. Okay, so let us look at the proof of this one. As T is normal, we have the approximate point spectrum of T and the spectrum of T are same, and we also know that the spectral radius of T and norm T are same. Now if you follow the earlier exercise, then we can conclude the result. So by the earlier exercise, we get that omega T equal to norm T. So this is about some important properties of the approximate point spectrum. Now let us look at self-adjoint operators in a different way from the numerical range point of view. So let us recall. Let us take a bounded operator defined on H. Then we have the numerical range of T as set of all inner product Tx with X, where X is coming from the unit sphere of H, and the numerical radius supreme of modulus inner product Tx with X, where X is coming from the unit sphere of H. If T is self-adjoint, then we know that the numerical range is subset of R, and also spectrum of T is subset of R. Now we want to see the relation between the spectrum and numerical range in this case. So for this, we define two bounds, lower and upper numerical bounds. MT is infimum of inner product Tx with x, where x is coming from the unit sphere of H, and capital MT, that is the supremum of inner product Tx with x, where x is coming from the unit sphere of H. We can easily show that MT times identity less than T less than or equal to capital MT times identity. That is, for every x in H, MT inner product MTX inner product with x less than or equal to inner product Tx with x, that is less than or equal to MT into inner product x with x. Okay, so or we can say that T minus MTI is positive and MTI minus T is positive. Okay, so the small mt is known as lower numerical bound. Capital M suffix T is upper numerical bound. T. We will show that spectrum of T is contained in the interval small mt comma capital MT. So let us prove this as a result. Let T be a bounded self-adjoint operator. Then we can say that spectrum of T is contained in the closed interval with endpoint small m suffix T comma capital M suffix T, and the second one is that both this upper and lower bounds, they are part of the spectrum. Okay. So first we want to show that the spectrum is subset of the closed interval mt comma capital MT. So what we show is that if lambda is outside this interval, we show that lambda cannot be inside the spectrum. So let us take lambda outside this interval. So that means lambda less than mt or lambda strictly bigger than mt. Okay, first assume that case 1 lambda less than mt. Then we have minus mt is less than minus lambda. So we can conclude that T minus lambda I is bigger than T minus mt times identity. Okay. Now we want to show that T minus lambda is invertible. For x in H, we have inner product of T minus lambda I x with x. This is bigger than, now T is bigger than or equal to mt, so this is mt minus lambda I. So x inner product with x for every x m. Now by the Cauchy-Squarge inequality, we can conclude that norm of t minus lambda I inner x multiplied by norm x is bigger than or equal to modulus of mod mt minus lambda norm x square. Or we can say that norm of t minus lambda I at x is bigger than modulus of mt minus lambda norm x. Now this quantity is strictly positive. So from this we can conclude that t minus lambda I is bounded below. Now t is self-adjoint, lambda is a real number. So from that we can conclude that t minus lambda is self-adjoint, hence once it is bounded below, it has a bounded inverse. This implies lambda is in the resultant of t. So whenever lambda is strictly less than mt, we have shown that t minus lambda is invertible. So with the same argument, we can show that if case 2 lambda is bigger than capital M suffix t, then lambda is, the proof follows in the same way, so we can avoid the proof here. So this completes the proof of 1. The second one, let us look at proof of 2. We want to show that M suffix t is in spectrum of t. Okay, so we have mt is bigger than mt. So we can assume that without loss of generality, mt is bigger than small mt, and we can assume that mt is bigger than or equal to 0. Okay, otherwise we can translate the operator with suitable constant and work with that new operator. Okay, so by definition, mt is supreme of modulus inner product tx with x, where x is coming from the unit sphere of h. Now by the definition of supremum, there exists a sequence xn in the unit sphere of h such that modulus of inner product t xn converges to mt. Okay. Now we want to show that mt is in the spectrum. It is enough to show that mt is in the approximate point spectrum of t. So we can look at, next consider t minus, we know the mt minus t is bigger than 0. Mt minus t, or we can say t minus mti inner product. Norm of this square is inner product t minus mti acting at xn with inner product with itself t minus mti. So this is nothing but norm txn square plus the last term is mt square norm xn square, that is 1 minus 2 real part of mt inner product txn with xn. Now we know that t is self-adjoint, so we can say that inner product txn with xn is a real number. So this is nothing but norm txn square plus mt square minus 2 mt inner product txn with xn. Okay. So this is less than or equal to norm txn square less than norm t square plus mt square minus 2 mt inner product txn with xn. Okay. Now with an appropriate subsequence, we can say that inner product txnk with xnk converges to mt. So we can choose a subsequence like that. From that we can conclude that this last term goes to mt. So okay. Now since we assume that mt is bigger than 0, and in this case when small mt is bigger than 0, so this automatically implies that t is positive. So in this case norm t and mt square norm t and mt are same minus 2 mt inner product txn with xn. So here we can choose a subsequence. This we have done earlier also. Choose a subsequence xnk of xn such that inner product t xnk with xnk converges to mt. So we can say that converges to some lambda where mod lambda equal to mt. But here we are assuming that mt is bigger than 0 and small mt is also bigger than 0. So in fact this implies that t is positive. Okay. Now this from this we can say that, so we can replace this by xnk. Instead of xn we can work with the sequence xnk. Now we can conclude that this goes to 0 because inner product txnk with xnk converges to 0. Okay. So this from this we can conclude that mt is in the approximate point spectrum of t and that nv is equal to the spectrum of t because t is self-adjoint. Okay. Now similar way we can also show that similarly we can show that small mt is also inside spectrum of t. Okay. So small mt is a lower numerical range, no, lower numerical bound, and capital M suffix t is the upper numerical bound. So we can conclude that spectrum of t is contained in uh, the interval with endpoints as lower numerical range and upper numerical lower and upper numerical range bounds. So we can actually show that the numerical range is a convex set and spectrum of t is contained in the closure of the numerical range. Okay. Now we want to see some more important results. we can easily verify that if T is self-adjoint, then show that norm of T is exactly maxima mod m suffix T, comma modulus of m suffix T. Okay. So let us see one example. Let us take T from C3 into C3, whose matrix with respect to the orthonormal basis is minus 2 minus 3. So this gives a self-adjoint matrix, and hence the corresponding operator is the self-adjoint operator. Now in this case, the spectrum of T is exactly the diagonal entries minus 1, minus 2, minus 3. We can easily show that in this case, we can easily show that mt is minus 3, capital M suffix T is minus 1, and norm of T is exactly 3, that is maxima modulus of M suffix T, comma modulus of M suffix T. Okay. So one more important observation. Let us take T to be self-adjoint. Then we can say that T is positive if and only if the lower numerical range of T or lower numerical bound of T is bigger than 0. If T is positive, we know that spectrum is positive, and the lower numerical range, lower numerical bound is also positive, because we know that inner product Tx with x is positive, so M sub x T is positive. On the other hand, we know that T is bigger than or equal to M sub x T multiplied by identity. So if M sub x T is positive, then automatically T is positive. Okay. So these are some of the important observations uh, related to the approximate point spectrum of uh, normal operators and self-adjoint operators. Now using these results, we will be representing compact operators as well as self-adjoint operators at a later stage. I'll stop here. Thank you very much.